The ultimate success of Project Mercury's manned orbital spaceflight program will result from the free world's concerted, concurrent efforts in scientific research and hardware manufacturing. Despite careful planning and design, malfunctions occur. The need for additional research and development is indicated by such failures. Data received for evaluation from this test on March 18, 1961 at Wallops Island, with spacecraft 14 mated to a Little Joe launch vehicle, pointed out need for improvement in several vital areas. Premature actuation of the escape rocket firing system prior to the spacecraft separation apparently was caused by the unscheduled closure of at least 2 of the spacecraft main clamp ring limit switches. Ground command separated the spacecraft and released the tower. The main and reserve parachutes were deployed. However, in spite of a descent rate 60% less than normal, the heat shield caused some damage in the area below the pressure bulkhead upon impact. After recovery, further investigation showed that only minor structural damage had occurred, and the spacecraft refurbishment for another flight was undertaken. At McDonnell Aircraft in St. Louis, the adapter ring fairing configuration was modified. Reducing its size improves the airflow around the spacecraft during powered flight. Components were fitted, welded, and riveted together. These sections were then carefully attached to the clamp ring fixture and labeled to ensure correct assembly. To eliminate recurrence of Little Joe 6's malfunction, arming relays were placed in the sequential system. These relays prevent a signal from the limit switches from firing the escape rocket motor until the clamp ring bolts have been detonated. Extensive vibration and acoustic testing assures quality limit switches for optimum operation during launch. Recovery of the spacecraft from the MR2 launch and subsequent inspection determined that some structural damage had occurred upon impact and the heat shield was lost during this stage of the operation. Space Task Group research led to a modification in the impact skirt support straps and the addition of retaining cables attached to the heat shield. A template fastened to the cable suspension ring aids in accurate location of the attaching holes. The titanium is tough and requires skill in drilling. A series of cables inside and these thin metal straps outside, both connected to the heat shield, were part of the STG design. Water stability testing of the new design model was conducted at the hydrodynamics facility at Langley. Qualification resulted from drop tests such as this. The operational stability of the reinforced lower bulkhead protection was confirmed. 6 water drop tests with spacecraft number 5 retrieved from the MR2 mission, plus 2 land impact tests at the Wallops Island facility, showed that no structural damage was experienced. Evaluation of these tests verified the STG modification in the event of an off-the-pad abort or emergency reentry and subsequent land impact. This flotation collar device was developed as a direct result of MR2's overshooting the programmed impact area and the need for spacecraft stability until recovery could be effected. Paramedics of the Air Sea Rescue Service applied the collar under actual at-sea conditions. In September 1960, testing of an explosive device for the emergency escape hatch was initiated. The hatch was installed on a production spacecraft in November and manually test fired to determine the blast effects on the cabin interior and structures. The redesigned hatch has completed all 10 qualification firings without failure, including one using a manned, pressurized spacecraft. In the high-altitude chamber at McDonald, spacecraft number 10 underwent the first test of Project Orbit, designed to investigate the operation of all spacecraft systems as an integrated unit on April 2, 1961. To date, over 38 hours of orbital flight simulation have been accrued. Possible systems limits have been investigated for periods in excess of 9 hours on an orbital mission. Further evidence has determined that by heating the retro rockets to 90 degrees Fahrenheit prior to liftoff, electrical heating in orbit will not be necessary as previously thought. Additional research and development conducted during April, May, and June of this year has assisted the Mercury program, and continued endeavors in this segment of the project are progressing now. With 13 spacecraft out of the original 20 called for under the McDonald contract, most of the major spacecraft construction has been completed. Modifications and equipment installations are progressing on schedule. Production spacecraft 15 has completed individual system testing. The necessary engineering changes in wiring of the antenna fairing separation sensor were being made, and the cabin interior was inspected. Recovery compartment equipment of number 16 was inspected, and the spacecraft was in the final stages of assembly. After being changed to a manned orbital flight mission, spacecraft 17's pressure suit transducer was installed. Reaction control system components were inspected, and the spacecraft entered the final steps of assembly. On capsule 18, a bevel was ground on a bushing near the bulkhead ring for fitting of the exterior shingles. Also in final assembly is spacecraft number 19. The manual control mechanism was installed in the cabin interior. The last spacecraft under construction, number 20, nears completion. Recovery compartment components have been inspected and the diode package installed. Post-flight evaluations continue to be made on spacecraft number 6, used in the MA2 flight test. Crews working round the clock have replaced reaction control system components on spacecraft number 8, and a new insulation blanket was installed after the MA3 aborted flight. With the Mercury flight program entering its major launch phase, the delivery of spacecraft and the subsequent post-flight checks and inspections, plus data analysis of flight behavior, also has become the major portion of spacecraft manufacturing as of this date. The complexities of adapting primarily a military missile to the manned spaceflight program of Project Mercury have continued to harass the Atlas launch vehicle's reliability flight tests. During this period, major changes have been made in the fuel flow design and have greatly increased the vehicle's capabilities for use in the orbital missions of Project Mercury. An anti-vortexing plate was developed from analyzed data of previous Atlas launches, showing that liquid oxygen sloshing within the booster fuselage was causing momentary bending in the rocket body. The plate is attached to the baffle shelf after inspection. With the addition of the anti-vortexing plate inside the rocket body, fuel flows through these many holes, giving a more even distribution, preventing spasmodic engine firing during liftoff and staging. Attaching holes are aligned and drilled, and the plate and shelf are integrated, ready for inspection. The MA3 programmer was recovered from the in-flight abort more than 30 days later. It had withstood both the landing impact and the inadvertent running over by a heavy truck. With reinstallation of some minor electrical parts and readjustment to the wiring inside, the programmer underwent a series of tests. It was determined that the overall reliability and construction of the mechanism had successfully experienced the abort, the impact, and the accident remaining in working order except for the smashed transistors and wiring. The sustainer engine for production model 109D was installed and inspected. The engine was connected to the afterbody of the booster, and upon completion of installation and preliminary checks, the launch vehicle was raised high above the production line and moved to the dock where complete system checkouts were conducted. At Wallops Island, the construction of Little Joe 7's booster was progressing. The outer shell or casing was installed around the rocket's body. This single-stage, solid propellant test vehicle was constructed and test flown during this report period. 2 Redstone launch vehicles were delivered during April for use in the suborbital flight tests of Project Mercury. While data analysis and evaluation continue on the MA3 programmer, spacecraft and launch vehicle integration systems checks are being conducted to prevent recurrence of the malfunction in the MA4 Atlas booster. The 3 astronauts selected as a team for the first suborbital mission of the flight program were subjected to extensive tests during April, May, and June. Refamiliarization with the expected Redstone G loads and the accumulation of biomedical baseline data was carried out at the Human Centrifuge Trainer at Johnsville, Pennsylvania. Each of the 3 flew at least 2 Mercury Redstone G profiles. Special restraint and biomedical data gathering equipment from NASA's Ames Research Center was used during these training runs. In conjunction with the training factors, these tests furnish aeromedical data recorded for comparison with actual flight profiles for further evaluation. The astronauts were thoroughly checked by flight medical officers for any evidence of physical impairment that might result in their injury or disqualification in the scheduled flight tests. Other Redstone flight profiles were run and rerun using the procedures trainer at Langley Field. Simulated systems malfunctions and abort profiles were injected into the spacecraft trainer, and the astronauts here again practiced switching to the various manual controls, backing up all of the spacecraft automatic systems. Roll, pitch, and yaw maneuvers were practiced using the manual control system's hand controller. Proficiency was gained in the use of this attitude control trainer. The 3-axis attitude simulations observed on this indicator familiarized the astronauts with flight roll, pitch, and yaw recognition. From 55 to 60 hours per week were spent by the astronauts in the procedures trainer number 2 at Cape Canaveral. Practice of the suborbital flight retro-firing sequence by the astronaut, the Mercury Control Center, and the Goddard computing facilities was conducted, although the Redstone missions will not achieve the speed for orbit where such firings will be necessary. Mercury control personnel underwent extensive training for the Redstone-boosted suborbital missions. This systems test allowed the Mercury Center, using the procedures trainer, to simulate actual flights for complete systems integration as well as operational training. Additional training was received by the astronauts as spacecraft communicators. Data was recorded in tapes made for use in tests of the tracking network for additional calibrations. With Project Mercury's flight program in its final qualification tests, the astronauts continue to practice in-flight coordination in high-performance aircraft and study aerial photographs and observation charts of both the Earth and the stars for visual recognition when in flight. Each Mercury flight is different, either in terms of the spacecraft, the launch vehicle, or the specific mission itself. And each astronaut continues to practice test runs on both static and stress devices to ensure that Project Mercury has the highest caliber test pilots with which to conduct its flight program. The ground tracking network, 18 stations in all, was completed during this quarter. Prior to the MA3 launch, the entire network was operational. the Bermuda station continued undergoing inter-systems checkouts. This facility is a duplicate control center with command control capabilities. The station was completed and ready for operation during the month of April. The final two stations to be completed were Kano, Nigeria, and Zanzibar. Simulated orbital flights using the procedures trainer at Cape Canaveral and test aircraft were plotted here at the Mercury Control Center. These tests of the entire network gave astronauts, Mercury Control Center personnel, and tracking station technicians additional training for the Mercury orbital flight program. The tests and the intra-systems checks are still being conducted to perfect familiarization with countdown procedures and handover control techniques. The delivery of production spacecraft number 14 to the Wallops Island facility initiated the flight test program for this period. During April and May, 3 spectacular flights were produced. The culmination of the entire Project Mercury program is dependent on the results obtained from hardware tested from both perfectly programmed and executed and unplanned malfunctioning flight tests. A maximum dynamic load test of the escape tower sequence at high altitude was planned for April 19, 1961. The modified spacecraft was mated with the Little Joe launch vehicle. During the launch, a hang fire developed in one of the Castor rocket motors. The resultant down-pitching of the test vehicle booster produced a much lower trajectory than was planned. The abort took place at 13,000 feet, at Mach 1.47. The main parachute deploy followed and disclosed that no structural damage had been experienced, either in the abort or in the landing. All test objectives are considered to have been met and exceeded. After delivery to the Cape Canaveral launch facility, spacecraft number 8 was unwrapped and underwent rigid systems checks and testing in Hangar S, from which it was moved to the launch site and raised for mating with the Atlas launch vehicle. The payload, a simulated astronaut, was scheduled to pass in one orbit around the Earth, and upon recovery and data evaluation, to have been the forerunner to a manned orbital mission. The escape tower is attached to the spacecraft. In the blockhouse, the first half of the countdown went smoothly. Telemetry equipment was checked and readied. Data recorded here was used for further evaluation of the Atlas launch vehicle and were influential in further systems. The spacecraft was thoroughly inspected and no structural damage was incurred, either from the high dynamic loads of the abort or the impact, and is presently being refurbished for another flight test. In the latter part of April, spacecraft number 7 was delivered to Cape Canaveral to Hangar S. After systems checks, the spacecraft with an astronaut aboard underwent pressure testing in the high-altitude pressure chamber. The Redstone launch vehicle to be used in the flight test was delivered, checked and tested, and then raised on the launch pad. Two days before the flight, the Mercury recovery forces put to sea. And this test was to be the free world's first manned space flight. The command ship, the aircraft carrier Lake Champlain, was to be the first solid thing the astronaut would touch after a scheduled 16-minute flight into space. Gallons of liquid oxygen filled the tanks of the launch vehicle, and the launch was scheduled for the early morning of May 2, 1961. Prevailing weather conditions, however, caused the launch to be postponed. But on May 5, the astronaut selected to be the first Mercury test pilot was transported to the launch complex. Months had been spent in physical and mental tests of his readiness. A backup astronaut had undergone the same schedule. Just 2 years and 7 months after the inception of Project Mercury, under the direction of the NASA Space Task Group, astronaut Alan B. Shepard traveled the 59 feet up the gantry, and at about T-minus 80 minutes, the hatch was secured. The countdown continued. Years of training, months of trial runs, days of tests, and hours of waiting, and now the links to the Earth were receding. The launch facility's recovery forces were deployed in the event of an early abort or malfunction. At T-minus 10 minutes, the recovery helicopters left for the impact area. As countless millions watched and listened with bated breath, the astronaut maintained manual control of the craft and almost continuous voice communications with Earth. At 9:34 in the morning, the Mercury Redstone 3 flight, with astronaut Alan Shepard at the controls, traveled 300 miles, reached an altitude of 115 miles, and experienced about 5 minutes of 0 G. Approximately 16 minutes after liftoff, the spacecraft, now dubbed Freedom 7, was located and recovered. The same helicopter picked up first astronaut Alan Shepard and then his Freedom 7 spacecraft. It delivered the spacecraft back to the deck of the carrier and finally landed to unload the free world's first spaceman. He received a "well done" from the President, acknowledging for free men everywhere their gratitude. Possible psychological factors resulting from the effects of weightlessness were discussed during the post-flight debriefing. After the preliminary checkup, the astronaut underwent 3 days of rigid testing and mental checks at the Grand Bahama facility. No ill effects from the flight were found. No modifications in the Mercury spacecraft were recommended by the pilot of this first space flight. All systems performed as expected in the MR3 mission. Now, additional Mercury suborbital flights were scheduled. As of this time, training for the astronauts in the stress devices is continuing. Through the continued research and development, training and practice tests, and data analysis of both launch vehicle and spacecraft recovered from space flights, major milestones in Project Mercury are expected in the near future.